recording and we're good to go. I graded your homeworks and posted grades along with feedback on that. I have not gotten to the labs yet. The labs were due last night, so I will get those graded sometime in the next few days. But I talked to a number of people while they were working on the labs, and it seems like those went well. There's the flakiness with Tinkercad, where sometimes the circuits don't want to reset from 9 to 0, and as I said, if that's the case, just go ahead and write up what you're seeing. And the way science works is, we've talked about this a little before. You have a hypothesis, you design an experiment to test that hypothesis, you conduct the experiment, you record your observations, and then you share those with others. So our hypothesis was, that we could use an AND gate and some inverters to reset this counter when it goes from 9 back to 0. And apparently that doesn't always work, right? And that's not a problem with digital logic, it's just a quirk with Tinkercad and the way we're setting it up. But, that's what you would report in your write-up of the experiment and in the presentation to the lab. You don't ditch the whole experiment, right? You put in your wiring diagram and you explain what you're doing and your system diagram and all that and draw your timing diagrams. But, in your discussion you say, but, for some reason the simulator didn't reflect this, and, the time in the upper left side of the simulator window stopped increasing as quickly as usual. It increased about 1 millisecond per second, which makes it seem like, something was unstable in the simulator itself. But that's all good. So I plan to talk about Lab 6 primarily today, and then go back to talking about state machine analysis. But any questions before we get to that? Anything you want to go over?
Not specifically material-wise in this class, but I have a question about choosing flat. And I'm supposed to be trying to enroll into engineering 270, but there's no option for that for the fall quarter.
Oh, 270 is not offered in fall. It's offered in winter and summer.
Okay, all right.
And summer is a good time to take 270 because, well, this doesn't affect us as much being online, but normally labs are done in an open lab setting, so you can go to the collaboratorium any time that it's open and work on your labs. But in summer session, the way classes are set up is typically there's 2 hours of lecture followed immediately by 2 hours of lab. And so you're pretty much guaranteed dedicated time, dedicated access to the computers, and dedicated access to your teacher. So summer's usually a better time, I think, for taking that than winter. With everything being online for this summer, I don't know if that's a big difference. But I usually recommend people do 270 right after they finish 250. As long as you've had CSE 121, because that's a prerequisite.
Is homework 5 long?
Homework 5, what homework did we just finish? 4?
Yeah, I think 5 is due Wednesday, but there's no 6 or 7 on.
6 and 7 I have not posted, but I thought 5 was due on Friday. Let's take a look. So homework for, that's due Wednesday. How's homework 5 coming for people?
I'm halfway done.
Anybody else? Because I can push it back. It is very, very long. Anybody gonna be upset if I push it back a couple of days?
Not at all.
Let's make that due Friday. just because we can talk about it today, but I definitely want to get you going on the lab today. So we'll have homework 5 be due on Friday, because that's the last, of the state machine homeworks. And then we'll deal with homework 6 later. You'll have about a week to do homework 6, but I'll post that. But lab 6 coming in due on the 29th. Okay, so that's I'm going to change that to. So lab 6, let's do that on June 1st, Monday. So homework due Friday, lab 6 due on Monday. Sound good?
Yes, sir.
Alright, so that gives us some room to breathe. Alright, other questions, comments?
Could you quickly go over full encoding versus hot encoding?
Yeah, we have not talked about that at all. So when we're doing state machine synthesis, we're told what kind of behavior we want. We want something that moves from this state to that state and so on. And part of the process is figuring out how many flip-flops you need. Okay, so let's say you have 4 states, A, B, C, and D. The most hardware efficient way to code this is to use 2 flip-flops. And our usual, idea that we can represent 4 different things using 2 bits. So we might use a representation like this. If both flip-flops are 0, we're in state A. If they're 0, 1, we're in B, and so on. That uses a smaller amount of hardware, right? It's only 2 flip-flops. But it has this possibly undesirable behavior that, for example, if we want to move from state B to state C, well, in state B, our flip-flops are going to look like this. And then our circuitry is going to say, oh, I should change our flip-flops to look like this. So this should turn into a 1 and this should turn into a 0. Those won't happen at the same time, right? So it's possible that this is going to change to a 1 first, and then this is going to change to a 0. Which means that in the brain of our state machine, we're actually going from state B to state C, but we're temporarily going to state D. Maybe just for a few nanoseconds, but very briefly we might be in that state. And that could be a problem. That could be the state that says, shut down the whole plant. And even if we're only in there briefly, right, it's a potentially bad glitch. So this is called full encoding. But there's an alternative, and this is called one-hot encoding. So hot is kind of an informal term for something that has voltage on it. So if you do wiring in a house, there's always a line that's considered hot. That's the one that's not carrying the ground level. So one-hot encoding is a coding system where only one bit is a 1 and all the other bits are 0. And so to code 4 states using one-hot encoding, we would use 4 flip-flops. And we would represent our 4 states like this. And we would design our circuitry so that any other value of the 4 flip-flops is considered invalid. And now if we want to move from state B to state C, we need to move from this value of flip-flops to this value of flip-flops. And if this bit happens to get set first, our circuitry will detect this as an invalid state and it won't do anything in response to it. The only valid states are these 4, and if this is our current state and this is our next state, no matter what order these bits change in, we're never going to go through another valid state. And so it can make more glitch-free circuitry at the expense of, in this case, using 4 flip-flops instead of only 2. So that's called one-hot encoding, and it's one of a number of options that you have when you're designing a state machine. And let me go back into Canvas. And let me post a pair of resources. State machine analysis and state machine synthesis. So this is just kind of a one-pager write-up of what we've been doing, right? So how do we analyze a state machine? Decide how many flip-flops you have. Okay, how many states you have, right? So if you have 4 flip-flops, typically you would be talking about 16 states, right? Name them, make a state assignment table. So what do the values of Q correspond to? How do those correspond to each state? Write equations for the flip-flop inputs in terms of the Q outputs and the external inputs. Okay, and write equations for the outputs in terms of the Q outputs and the external inputs. So you write your equations, and then you make this big long state transition table. Okay, so 1 row for each input and state combination. List the current Q output values for the given state, and so on and so forth. So this is what you were doing in the homework set that you just got back. Okay, and so question 11, for example, you had this circuit you were working with. So the analysis process, decide how many states you have. Well, there's going to be 4 states because we have 2 flip-flops, right? Flip-flop 1, flip-flop 2. And we haven't really been naming them. I've just been calling our states, like Q1, Q0, for example. But you could name them A, B, C, D and make a table that says something like, A is 0, 0, B is 0, 1, and so on. But then write equations for the inputs to the flip-flops in terms of the outputs. Okay? So output, 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 output of the flip-flop, external input. So as a function of those variables, we want to write equations for J0, K0, J1, K1. And this is tracing wires and carefully writing. So a couple of things I saw on the homeworks. One, a lot of people did not use an exclusive OR for this. They just use an OR. The 2 lines over here, that means it's an XOR. Okay. There's our Tuesday landscaper one. All right. And remember, when I draw these, I put little symbols in here. There's an OR gate, there's an AND, there's an AND, there's an XOR, there's an AND. Don't have to do that, but for me, it kind of helps me keep track of what's what. The other thing I saw was this J0, right? J0 is a kind of complex signal. It's coming out of a NOR gate. Okay, so it's going to be something ORed with something with a bar on top. Don't drop that bar on top. One of the inputs right here is Y1 bar or Q1 bar, so that's this. And the other input is coming from the output of this AND gate, which is Q0 bar ANDed with X. So Q0 bar ANDed with X. And some people simplified that, because that's a lot of bars. Personal observation, writing bars on top of variables is less ambiguous than putting the quote mark after them. Okay? If you're typing, we can't easily put a bar on top, so we use a quotation mark. But if you really just want to draw on paper, X complemented, I would suggest sticking with a bar, because it really goes with the X, and if you see something like YX bar, you might be tempted to think this is, that, which it's not, right? If you do this, or you do this, right? They're clearly different things. Anyway, a lot of people seem to be using quotation marks even when they're writing on paper. So if that's confusing to you, think about going back to using bars on top. De Morgan's theorem, right, says that a NOR is the same as an AND when you complement the two things being NORed. So A or B bar is A bar ANDed with B bar. So by De Morgan's theorem, this would be Q0 bar X all barred, right, ANDed with Q1 bar barred, right? So this thing is my A, this thing is my B. A or B bar is equal to A bar, so this thing barred, ANDed with B bar, so this thing barred. Okay, which is Q0 X bar bar, ANDed with, and Q1 bar bar is just Q1. Alright, you can get rid of this double negation here, but you've got to use De Morgan's theorem again. You can't just complement both of these, and a lot of people turn this into Q0 ANDed with X bar, and that's not the same thing. Okay, so one more instance of De Morgan's theorem. Q0 bar ANDed with X bar is the same thing as, well, what's De Morgan's theorem in this form? AB bar is A bar or B bar. So this is A, this is B. So it says I can complement this, and I can complement X, and I can change the AND into an OR. And now that's just going to be Q0 ORed with X bar. So we can change J0 into this much simpler form, right? But you've got to do some work to do that. It's probably worth it because this is easier to work with in terms of truth tables, right? But you're using De Morgan's theorem twice, you're doing double negations and so on. Whatever you decide to do, if you end up with this, you got to show your work, okay? If you just say J0 equals this, and this is the equation, right? How did you turn J0 into an OR of two terms when it's coming out of a NOR gate, right? And that's coming out of an AND gate and so on and so forth. So show your steps, okay? So write equations for the flip-flop inputs and for the output, okay? There's the flip-flop inputs, there's the output of the circuit. And then make a state transition table, okay? So what is a state transition table? You're looking at your present state, that's the current value of Q1 and Q0, and you're looking at the present value of the inputs. Okay? Based on these three values, write down what the output is, right, using your formula. And then figure out what the inputs to the flip-flops are, so J1, K1, J0, K0. And then use your knowledge of flip-flops to say, okay, if J1 and K1 are both 1, then flip-flop 1 is going to toggle when the clock ticks. What's the current value of flip-flop 1? It's currently a 0, so the new value is going to be a 1. Okay, J0 is 0, K0 is 1. If you put 0, 1 into a JK flip-flop, the next clock tick, the flip-flop's going to go to a 0, so the new value of that flip-flop is 0. So you have to do 8 of these analyses to find the new value of Q1 and 8 of these to find the new value of Q0. Okay, this is why these kinds of questions are so long. So you do that, list the flip-flop inputs, list the next value of Q based on those, and list the next state based on those. So the punchline from this table is, if I'm in state 0, 0, my input is 0, my output will be 0, my next state will be 1, 0. If I'm in state 0, 0, my input is 1, my output will be 0, my next state will be 1, 0, and so on. Okay, and then from that, you make your state transition diagram. If you're in state 0, 0, and your input is 0, your next state will be 1, 0, and your output will be 0. If you're in state 1, 0, and your input is 1, your output will be 1, your next state will be 0, 0. How do I know that? Because that's what I got here. If I'm in state 1, 0, and my input is 1, my output is 1, my next state is 0, 0. So this is the diagram that visually captures all of this stuff, right? This is really hard to look at and know exactly what your machine is doing. This is much easier, right? If you start in state 0, you're always going to go to state 1 next. If you're in state 1, you're either going to go back to 0, sorry, you're going to go to 2. You're either going to go back to 0 or go over to 3. And once you're in state 3, you stay in state 3. You're there forever. Doesn't matter what your input is. And nothing ever takes you to state 1, but if you happen to start in state 1 and your input is a 0, then you go to your final state 3. Right? So this is always what you're after. And you need a key, right? So that I know this 1 means X is 1, this 0 means that Z will be 0. This will be Q1 and Q0. Right? So state machine analysis is saying, you know, here's a circuit, what does this machine do? Here's your answer. Okay. Synthesis is the other direction. Here's what I want my machine to do. Do the work, do the work, do the work. Here's a circuit that does that. So we're going to start from a state diagram. We're going to go to a state transition table. We're going to turn that into a set of equations, and then we're going to sketch a circuit. So I've also posted a summary of those, which is state machine synthesis. So step 1, decide how many flip-flops you need, which is back to this question of one-hop encoding versus full encoding. We generally do full encoding. So decide how many flip-flops you need, what kinds you need, which you're typically told in a problem, or it might be, you know, I've got a bunch of T flip-flops, so I'm going to use those. Figure out what you're going to call each of your flip-flop combinations, and then make your transition table. List the outputs and then the flip-flop inputs that you need to make each of those. So list the flip-flop input values based on the present state and the desired next state and what type of flip-flop it is. And then you've got just a good old truth table like this. And so you write equations for J1 equals, K1 equals, J0 equals, K0 equals, and Z equals, right? By doing sum of products, K-maps, whatever, that gives you these equations. And then you sketch a circuit the way we always do. So those two resources are posted on Canvas under resources, so state machine analysis, state machine synthesis. All right, so let's see, we got questions in here. I'm still having trouble trying to link up the CD 4511 7-segment components with the circuits I make. I keep losing vital lab points because of it, and it's really annoying when my circuits do not work. I don't think I'm dinging a whole lot of points for how that's hooked up. I'm very interested in seeing it in your wiring diagram, right? But if you hook it up and it's simply not working, that's going to cost you a few points, but it's the process. So yes, someone says it can be tough if you get one wire wrong, it makes it act super whack. That is totally true. So my suggestion would be come by during office hours and screen share. Let me see your circuit in Tinkercad, and let's start tracing wires. But let's take a look at the 4511 again. And there's three pieces to this, okay? There's these controls that you have in the beginning, LE, BL, and LT. LE needs to be low, BL and LT need to be high. Okay? This is like lamp enable, and it's active low. So we want that to be low so that the lamp is enabled. Okay? If this is high, then the circuit will do something else. So LE bar should be low. So that's pin 3. Pull pin 3 to ground. Okay, direct wire. And then 4 and 5 should be high. Okay, 4 is pulled low to blank the whole output. And 5 is a lamp test. If 5 is pulled low, all of the segments go on. So that's what you use to test to see if anything's burned out on your 7-segment display. So it'll display the letter 8, digit 8. So so BL and LT have to get pulled high. So pins 4 and 5, pull those high through a 1K resistor. Okay. Ground goes directly to pin 8. 5 volts goes directly to pin 16. And then you put your input. Oh yeah, 3 and 4 high, 5 and ground. Okay, that probably will not work. Nope, you were right. You were right. 3 and 4 go high, 5 goes to ground. So let me put this in writing. So LE bar should be low, and BL bar should be high, and LT bar should be high. So I'm just copying these from the truth table. And then translate those into pins. So LT bar is pin 3, BL bar is pin 4, and LE bar is pin 5. So pins 3 and 4 go through a 1K to 5 volts, and pin 5 goes to ground. Thank you. All right, and then you want to feed the input that you're trying to display to pins 7, 1, 2, and 6. Okay, in that order. So least significant bit. This is QA, QB, QC, and QD. Go to pins 7, 1, 2, and 6 respectively. And then those 7 pins on the output side go to the A, B, C, D, E, F, G pins on the 7-segment display. The other detail on hooking this thing up is make sure you use the right kind of 7-segment display. So if you click on this in Tinkercad, you can choose common cathode, common anode. You want common cathode. Okay, if you do this in the actual lab, the devices are what are called common anode, which means the common line gets set to power. But here you want to set the common lines to ground, and then putting 5 volts into one of these segments lights it up. So I have lab hours at 3 o'clock every day, and Tuesday, Wednesday, Thursday also at 11 o'clock. So yeah, definitely come by and we can look at Tinkercad setups and figure out what's going on. And once you get one of these working like once or twice, then it's relatively easy to make them work after that. It's really the first few times trying to set it up that it's particularly confusing. But once you've done it and you believe that it'll work, that's half the battle in making it work next time. All right, cool. Other questions? Alright, so I'm not going to talk about the next homework because you're still working on homework 5. And we'll run through that homework and see what else. How many more labs are due till the last week? So lab 6 we're going to talk about right now, and then there's one more, lab 7. Lab 7 does not involve Tinkercad though. Lab 7 is always a software lab, even in person. Quarters, because after state machine synthesis we're going to start talking about something called Verilog, and we're going to use some software to simulate Verilog circuits, and it's going to feel very different from everything else we've been doing. It's not going to involve a lot of truth tables and things like that, and so there's a lab to go with that. Lab 7, that's the last lab for the course. So lab 6 we'll talk about right now, and then one more lab after that. And we have 3 weeks left. So we have 6 class meetings left, including today, and then final exam after that. But we're at a good place in the course, right? We'll finish talking about synthesis today. We'll probably start talking about Verilog on Thursday. And that'll leave us a couple of weeks to dig into Verilog, and then a week to kind of like wrap stuff up at the end. All right, Lab 6. Lab 6 is the completion of the traffic light control system. And we're going to add yellow lights, and they're going to be timed. And it's like really cool when it works. And I've never seen this done in Tinkercad before, so this will be extra bonus exciting. So there's 2 experiments here. The first experiment is a building block of the second experiment. It's a delay circuit. Okay, so design and implement a 2 to 4 second delay using the 7474 and the 555. Assume the 555 is configured to generate a 2-second pulse, which it already is. Okay, that's what you've been doing in this previous lab. You set it up to generate a high signal and then a low signal, and that pattern repeats every 2 seconds roughly. So you've already got the 555. Let's look at the 7474. So the 7474 is a set of flip-flops. So it's these dual positive edge triggered flip-flops. So we haven't really looked at a data sheet yet. Let's look at these. 7474 dual positive edge triggered D flip-flops with preset, clear, and complementary outputs. Okay, you always have all these mouthful of words with flip-flops. Here's one flip-flop. Okay, on the left here. There's the clock input. So the clock input comes from clock 1. There's a Q output, which is labeled Q1 bar. There's a positive Q output, which is labeled Q1. And there's a D input labeled D1. And there's also another pair of inputs. There's something labeled clear 1, which goes through an inverter and goes in the top. And then there's preset 1, PR1, which goes through a bubble and into the bottom. So what do these things do? Look at the function table. Okay, if preset is low and clear is high, your flip-flop goes high. Does not matter what the clock's doing, does not matter what the D input is. Okay, as soon as you pull this preset line low, the output goes high. On the other hand, as soon as the clear line goes low, the output goes low. So these are active low asynchronous inputs. Okay, active low meaning if this is a clear input, it will clear when this input is 0, when it's low. And asynchronous meaning it does not wait for a clock tick to take action. As soon as this input goes low, the flip-flop clears immediately, even if the clock hasn't ticked. Now those 2 sentences that we just said can't both be true all the time. Because I just said if this is low, the output will go high. If this is low, the output will go low. Why is it when PR and clear are low, then outputs go high? Right, so you're ahead of me. These can't both be true, because what I've said is when this goes low, the output will be high. When this goes low, the output will be low. Well, what happens if both of them go low? Right? The output cannot simultaneously go high and low. Something will happen. Okay? What's going to happen is you're going to get into this weird state where the output is high, but the complemented output is also high. Okay? This configuration is non-stable. Okay? This is kind of a forbidden state. I mean, it won't physically stop us from making both inputs low, but it's considered a sort of not a state that you would normally use. And they have this asterisk here saying that when either of those inputs goes high again, this is not what the output will be. Okay? But it's hard to predict what the output will be. So it's an unstable state. And why are they both high? That's the way that the internal circuitry is responding to this particular set of input values. And it's probably more an artifact of how the circuit was designed rather than an actual feature that was built in. The understanding is we're not going to try to preset it and clear it at the same time. Right? So it's like, you know, press this to turn the light on, press this to turn the light off. Right? What if you press both buttons at the same time? Right? I tried to do this in my house when we first moved in because we had these buttons that would pop out of the wall when you pressed them. And, you know, the answer is unpredictable. Your parents say, hey, don't do that. But the normal state in which this operates, so that was a good question, by the way. The normal state in which this operates is these presets are high, okay? Since the bubbles here, it's saying these are active low. So if they're low, this says clear, this says preset. So normally we put those both high, and now the behavior is sort of our typical D flip-flop. When the clock rises, if the input's high, the output goes high. When the clock rises, if the input is low, the output goes low. And if the clock is not changing, the D input is irrelevant and the output is totally stable. And here they're showing Q0 to mean the output level of Q before the indicated input conditions were established. So before the clock tick, we have Q0, the current value of Q is going to be the same. So this is the same D flip-flop that I've been telling you about, except it's got these extra preset and clear inputs. Alright, so how do we get a delay of 2 to 4 seconds out of some D flip-flops? So we can make something called a shift register. And shift registers are a standard piece of digital logic. You can buy chips that implement shift registers. When I was a kid, Radio Shack sold a very long shift register. It was, I think, 128 bits or something. And you could use it to make a very long delay that you could hook into a guitar amplifier, and you could make an echo effect, right? By taking your sound and causing it to take some time to travel from input to output, you could add an echo. Can I refocus? Yes, I can try. How's that? Alright, so shift register. So let's think about this circuit. So these are D flip-flops. They're going to be clocked together. And I'm going to feed an input into this D. And I'm going to feed the second Q to an output. And I'm going to connect the first flip-flop's output to the second flip-flop's input. And let's look at what this does. So let's imagine a clock that's just going up and down, up and down, up and down all day long. And let's imagine an input that is 0. And then at some point before the next clock tick, I'm going to raise the input to a 1. And I'm going to leave it high for a little while, and then I'm going to drop it back to a 0. Okay, let me call this output middle. And let's suppose that middle, starts off at 0. Okay, I raise the D input. Nothing changes until the next clock tick. At the next clock tick, this D flip-flop is going to look at that D input. It's going to say it's a 1. It's going to set its Q output to 1. So right here, and I'm ignoring propagation delays and stuff. Right here, this middle line is going to go up to a logic 1. Well, that middle line is the D input on this flip-flop. But when the clock ticked right here, what was the D input to this flip-flop? It was a 0. Okay? This middle line did not raise until after the clock ticked. So at the moment of the clock tick, this input was a 0. Which means the output is going to continue to be a 0. until the next clock tick. Now at this clock tick, this second flip-flop's going to say, what is my D input? Oh, it's a logic 1. Okay, I'll set my output to a logic 1. And now my output's going to go high. But notice what happened. Here's where the input went high. Here's where the output went high. That's a significant time delay. It's a time delay of a little over one of these clock cycles. So if this is a 2-second clock, if the time from here to here is 2 seconds, this means we raise the input, and about 2 seconds later, the output goes high. Okay, what happens when the clock drops? Well, the clock dropped right here, but nothing's going to happen until the next clock tick. At the moment of that clock tick, two things happen. One, the first flip-flop says, hey, clock just ticked. What's my input value? It's a 0. Okay, I'm going to set my output value to a 0. At the same moment, the second flip-flop is saying, hey, the clock just ticked. What's my input value? My input value is a 1. I'm going to leave my output at a 1. And then nothing happens until the next clock tick. But this next time the clock ticks, flip-flop 1 says, hey, what's my input value? 0. I'll leave my output at 0. Flip-flop 2 says, what's my input value? It's a 0. Okay, I'll change my output to a 0. And it does that. So if we just look at input versus output, we've got a delay circuit. Okay, this is powerful. Raise the input from 0 to 1, and you know, for a couple of seconds, nothing happens, then all of a sudden the output jumps up. Drop the input from 1 back to 0, and nothing happens for a few seconds, then all of a sudden the output drops down. So this simple circuit, just two flip-flops hooked up like this with a common clock going to both, implements a delay. If we wanted a longer delay, we could slow the clock down, or we could make more stages to this flip-flop, this shift register. If we had another stage over here, right, this input needs to get loaded into here on a clock tick, and then loaded into the next flip-flop on the next clock tick, and then loaded into a third flip-flop before the third flip-flop's output responds. And basically each time the clock ticks, whatever values we have in these flip-flops is going to move down one step. And this is happening because of the synchronous clocking. So let's draw a bigger picture. So D and Q, D and Q. And all the clocks are connected together. And let's say this has a 0, 1, 1, 0. When the clock ticks, what's going to happen? This is going to move into here at exactly the same moment that this moves into here and this moves into here. And whatever input we have over here moves into here. If these were gates, if these were latches like we first started developing, and we raised the load line, this would go into here and over to here and over to here and over to here and would run through all of these latches, and each of them would have this value. But with flip-flops, because they are edge triggered, at the moment when the clock ticks, this is going to say, oh, my input's a 1, that's going to become a 1. This is going to say, oh, my input's a 0, it's going to become a 0. This is still going to say my input's a 1, it's going to become a 1. So this is going to become, you know, whatever that was, and then a 0, and then a 1, and a 1. So it shifts. And each time we tick the clock, things move down one spot. And that's a really powerful circuit. And it uses this idea that all these things are clocked at the exact same moment. All right, so that's experiment 1. And you want to build a circuit in this spirit. And here's what should happen, right? So your clock comes from your 555 pin 3. And you can put a switch on this input, right? Pull it up through a 1K resistor to 5 volts. And your output you can run through an LED. So hook up your 555 to your clock, put a switch in the usual way to your first input, put an LED on your output. Here's what you should see during the simulation. What was the first symbol on the left? You mean this thing? It's whatever value happens to be going into there. Could be a 0 or a 1. It's a nebulous cloud symbol. So build a circuit, start the simulation. Here's what you should see. Close the switch to set this to a 0, your LED should go off. Open the switch to set it to a 1, and 2 to 4 seconds later, your LED should turn on. Not immediately though. Okay, put a 1 in here by opening the switch, and 2 to 4 seconds later, your LED turns on. Now close the switch to put a 0 in there, and it'll take 2 to 4 seconds before the LED turns off. Okay, that's the effect that you're after. So what do you want to do for this experiment? You want to discuss all of this. You want to, sketch out what you're trying to do. You want to make a wiring diagram with part numbers and pin numbers and all of that stuff. And then implement it in Tinkercad and then see if it works. How do you see if it works? Well, what I just described, right? Close the switch, LED should be off. Open the switch, it should take a few seconds for the LED to turn on. So time it, right? And once the LED's on, close the switch. Should take a few seconds for it to turn off. And it should be noticeable. It shouldn't be just, a fraction of a second. It should be at least 2 seconds. Now, how long does it actually take for that to happen? Well, it depends, If I change my input right before the clock tick, then my output's going to change 1 clock tick later. Right? So if I change my input right here, then the next clock tick right here where the output changes, it's about 2 seconds. But if I change my input right here, right, nothing's going to happen till this clock tick, which is where it's going to get loaded into the first flip-flop, and then the second clock tick, the output's going to change. So if I change right after a clock tick, it's going to be 1-2 cycles, about 4 seconds. If I change right before a clock tick, it's going to be 1 cycle, which is 2 seconds. So that's the 2 to 4 second part in the lab, using a 2-second clock pulse. And you can't control whether it's 2 seconds or 4 seconds, it just depends on the timing of it. All right, any other questions on that part, experiment 1? Just curious, how would you know the ground how do you know to ground the LED from any kind of flip-flop? You mean like this ground right here? Basically, I just want to see what the output is, right? And so anytime I want to see what a logic level is, I can run it through an LED going in the forward direction, connect the other end to ground. And now if I have a logic 1 here, the LED will turn on. If I have a logic 0, it'll turn off. And that's the usual way to look at a voltage level using an LED. But in the lab, I could just put a multimeter on here and measure the voltage. Or I could hook an LED backwards, and it would be on if this was a 0 and off if it was a 1, and so on. If that makes sense. All right, so let's take a 5-minute break, and then I want to take another look at the counter that you're using in Lab 5, and then we'll talk about Experiment 2 for Lab 6, which will be adding a yellow light to our traffic control signal. So I'll come back in about 5 minutes.